Hello everyone, welcome back to this quick introduction to number theory. In this video, what we're going to be talking about is about congruence classes and the integers modulo m, the set of integers modulo m. So just as a reminder, this is how we defined congruences. We say that A is congruent to B modulo M if M divides their difference, M divides A minus B. So let me repeat this here. That A, oops, let's not use the calligraphic pen anymore. We say that A is congruent to B modulo M if and only if M divides their difference. Right. So here's something that I think I mentioned in one of the previous videos, is that if you fix modulus m, and if a is an integer, then we can find the class of a modulo m by doing long division by m. So if I do long division, there would be a quotient q and a remainder r, and long division assures me that this remainder will be between 0 and m, and if so, then A is actually congruent to R modulo M, and this R is what we call the least non-negative residue of A modulo M. Okay, so we used that in the previous videos to find the congruence classes of some numbers, and so let me show you this again. That so if we had 35 and we want to find the least non-negative residue, say modulo 12, then what we can do is write divide by 12. 12 times 2 is 24 plus 11, and that tells me that 35 is congruent to 11 modulo 12, and 11 is the least non-negative residue of 35 modulo 12. Great. Now, this tells me also that every number is going to be congruent to one of these possible remainders. So every integer is congruent to a number between 0 and m minus 1. So note then that every number, every integer is uniquely congruent to one of 0, 1, 2, 3, up to m minus 1 when reduced modulo m. And what that means is that the congruences partition the integers into a finite number of subsets. So the upshot is that the integers are actually partitioned into the set of numbers that are 0 modulo m, union the set of numbers that are 1 modulo m, union all the way up to the numbers that are minus 1 modulo m, or m minus 1 modulo m. And so what we are going to actually do is create a number system based on this, such that the elements of my number system are actually these sets of congruence classes. So this is called, each one of these is a congruence class. So for example, the congruence class of 2 modulo 7 is it's the class of all the integers, or the subset of all the integers that are 2 modulo 7. So for example, 2 is there, and if I add 7, I get another one, 9. If I add 7, 16, and if I add 7, what is that, 23, etc. Those are in that set, but also the negative integers that I get. So 2 minus 7, that's minus 5. Minus 7, that will be minus 12, and etc. Okay, so that is the congruence class of 2 modulo 7. And what happens is that the integers are partitioned modulo 7 into 0 modulo 7, and the class of 1 modulo 7, to the class of 6 modulo 7. So there is exactly 7 subsets that partition the integers into these 7 subsets, and every number is exactly in one of these classes. And what we're going to do is define an object or a number system called Z mod MZ, such that these subsets are going to be the elements. So we're going to define an operation so that we can work with these subsets as if they were numbers themselves. So here's what we do. We write Z mod MZ for the set of congruence classes modulo M. So there is a class of 0 modulo M and 1 modulo M and up to M minus 1 modulo M. And we are going to define operations on congruence classes as follows. We are going to define an addition. If I want to add the class of A modulo M to the class of B modulo M, what I can do is add A and B and then reduce modulo M and see what class that is. And if I want to multiply, I can multiply the class of A with the class of B by multiplying their representatives and then reduce modulo M. So let me show you what that looks like when I look at M equals 3. So I'm trying to just look at the classes modulo 3. There are exactly 3 elements: 0 mod 3, 1 mod 3, and 2 mod 3. And there is an addition and there is a multiplication. But the beauty of these is that they are finite sets. It's a finite set with exactly 3 elements. And I can do addition. So I can actually write a complete addition table over the integers. When we start learning as kids, we find some addition tables of small numbers and multiplication tables of small numbers. But here, this is an addition table of all the numbers in Z mod 3, all the elements. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2. 1 plus 0 is 1, 1 plus 1 is 2, but 1 plus 2 is 3, and 3 is the class of 0 modulo 3. So I get 0. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 1 is 3. So 3 is the class of 0. And 2 plus 2 is 4. That's the class of 1. So this is the complete addition table in Z mod 3. And I can do the same for multiplication. 0 times 0 is 0. 0 times 1 is 0. 0 times 2 is 0. 1 times 0 is 0. 2 times 0 is 0. 1 times 1 is 1. 1 times 2 is 2. 2 times 1 is 2. 2 times 2 is 4. And 4 is 1. So I get this multiplication table. And again, the beauty is that this is just, it looks like addition and multiplication in the integers. And it has very similar properties. But this is just a toy version of the integers, and it's just a finite version of the integers. So for computation and for eventually cryptography, this is very useful. This concept is very, very useful. Okay, so let's see, what are we going to do next? So in this new system that we've created, there are some elements that have multiplicative inverses, and those are going to call. Let's define what is a multiplicative inverse. We've already discussed a little bit about that in the previous video. So the elements, so we say that A modulo M has a multiplicative inverse modulo M if there is a class B modulo M, so some integer B, such that A times B is congruent to 1 modulo M. So we recall that in the previous video, we saw that if the GCD of A and M is 1, then B exists, and it is in fact unique. Let me give you an example of that. So, for example, 3 is or has a multiplicative inverse modulo 7, because remember, we actually first found out that 3 times minus 2, that is minus 6, and that is 1 mod 7. And minus 2 is congruent to 5 modulo 7. So this means that 3 times 5 is 15, which is 1 modulo 7. So 3 is invertible mod 7, and its inverse is 5 mod 7. Okay, so we have multiplicative inverse, and we actually are going to call those, we're going to give them a name. We're going to say those are units. Okay, so the elements of Z mod MZ that have multiplicative inverses, that have multiplicative inverses, are called units. I.e., A mod M is a unit if and only if there is some B mod M such that A times B is 1 mod M. Now, and we denote the units of Z mod MZ by, usually we write Z mod MZ star, or Z mod MZ cross, like this. Okay. One note is that in the integers, Z has exactly 2 units. Plus or minus 1 are the only elements that have another integer, such that when you multiply it, you get 1. But in the integers modulo M, you might have multiple elements that are invertible. And if you go up to Q, in Q, every non-zero element is a unit, right? Because if M over N is non-zero, then n over m is its inverse, the multiplicative inverse. So we are somewhere between the integers that only have 2 units and q, where everything that is non-zero is a unit. Z mod mz sometimes has a few of them are units, and some times everything that is non-zero is a unit. That is a very nice case when everything that is non-zero is a unit. We call those fields. So we're going to try to figure out when do we have that one of these congruence classes groups, Z mod mz, actually forms a field, just like the rational numbers, just like the reals, just like the complex numbers. Okay, so now it turns out that you can figure out, because of what I said before, because of this note here, the units are precisely those elements that are relatively prime to the modulus. So it turns out that Z mod mz cross are those classes modulo m whose GCD with m is 1. So those numbers that are relatively prime to m will have multiplicative inverses. So for example, in Z mod mz, if m is 3, I'm looking at Z mod 3z, and I want to compute 3 mod z cross, that will be the class of 1 and the class of 2. Because, well, 1 times 1 is 1, so 1 is its own multiplicative inverse. And 2 times 2, from the table that we came up with, 2 times 2 is 4, that is 1, modulo 3. So 2 is also its own multiplicative inverse. Okay. But however, if you go to other moduli, so for example, if m is 12 and we look at Z mod 12z, then the numbers or the congruence classes that have inverses are, so remember, this is the class of 0, 1, 2, up to 11, modulo 12. The ones that have inverses are those that are relatively prime to 12. So 1 is relatively prime to 12, not 2, not 3, not 4. 5 is relatively prime, not 6. 7 is, not 8, not 9, not 10, but 11 is. So there are 4 units, and we can check that those are actually units because, well, 1 times 1 is 1. 5 times 5 is 25, which is 1 mod 12. So 5 turns out to be its own multiplicative inverse. That's not always the case, that a number will be its own multiplicative inverse. 7 times 7, it turns out also is 49, which is 48 plus 1. And 11 times 11, that is minus 1 times minus 1, and that is 1, all of these mod 12. So it turns out that all of those are their own multiplicative inverses. Let me show you something that also has a few units, but not everything is its own multiplicative inverse. So if we look at Z mod 10, Z mod 10 cross the units are 1, 3, 7, and 9 modulo 10. And you can check that 3 times 7 is 21, which is 1. So 7 is the multiplicative inverse of 3, and 3 is the multiplicative inverse of 7. And 9 times 9 is 81, so that is 1. So these are congruences mod 10. So here, by the way, we will write sometimes that 7 is the multiplicative inverse of 3. But note, warning, that here 3 to the minus 1 is just some notation. So this is not a third, the rational number 1/3. That is just some notation to say that the number 7 is the multiplicative inverse of 3. But it does not say that has to do with the number 1/3. It's the same concept because 1/3 is a multiplicative inverse of 3 in the rational numbers, but here the multiplicative inverse of 3 is actually the number 7, or the congruence class of 7. Okay, what else? What happens if we do something like, if we look at Z mod 4001? So it turns out that 4001 is prime. So if I try to compute the units, the number 1 is relatively prime to 4001 because it is 4001 is prime, so it has to be. The number 2 is, the number 3 is relatively prime, the number 4 and the number 5, etc. Every number up to 4000 will be relatively prime to 4001, and 4000 is 4001 minus 1, so I'm done. So everything modulo 4001 is a unit. So every non-zero congruence class modulo 4001 is a unit. So in here, this number system works very much like a field, like the rationals, or like the real numbers, or like the complex numbers. I have an addition, I have a multiplication, they're commutative, associative, distributive, and every number that is non-zero has a multiplicative inverse. So it looks very much like Q, like the real numbers, like the complex numbers, but this is finite. There's only a finite number of elements, so it's our first example of a finite field. Okay, and in general, what we have is that if P is prime, then Z mod PZ cross the units modulo P are precisely the classes 1, 2, 3, up to P minus 1 modulo P. So every class that is non-zero is a unit. Okay. In general, how many units are there? That's a slightly tricky question to answer. And what we do is use something that Euler found. And it turns out that the Euler phi function, Euler's phi function, it does exactly the job of counting how many units are there modulo m. So the function phi of an integer m is defined to be precisely the number of units in the number of congruence classes modulo m that are units. So this is exactly the numbers between a and m that are relatively prime to m. Because remember that we said that if a and m are relatively prime, there is a unit, and it's actually if and only if. So the Euler phi function counts exactly how many elements between 0 and m are relatively prime to 1. So we have, we set up phi of 1 to be 1, and then we can compute other values. For example, phi of 2, how many congruence classes modulo 2 are units? Just the number 1. So just 1. How about phi of 3? Phi of 3 modulo 3, we already saw that 1 and 2 are units, so there are 2. How about phi of 4? Well, for phi of 4, we have to do a little computation here. Let's see, what are the numbers? 1, 2, 3. between 0 and 4, there is the numbers 1, 2, and 3. And how many are units? 1 and 3 are units, so there is exactly 2 units. Okay. Phi of 5, 5 is prime, so everything except 0 is a unit, so there's going to be 4. Phi of 6, you can check that there's 2, and more generally, actually, if we have a prime, we've said that everything except 0 is a unit, so phi of p is p minus 1. And we can use that and another formula to compute values of the Euler-Phi function as follows. So, so first, if p is prime, then phi of p is p minus 1. If p is prime and n is bigger or equal to 1, then we can you can prove that the number of units modulo p to the n is p to the n minus 1 times p minus 1. And finally, if the GCD of m and n is 1, then phi of a product of relatively prime numbers is the product of the phi's. We say that phi is a multiplicative function. Okay. So for example, I'm not going to prove these, but you can use those to find what is the value of phi of 100. So phi of 100, the first thing you do is factor 100, that is 4 times 25. Okay. And because 4 and 25 are relatively prime, I can do phi of 4 times phi of 25. Again, because they're relatively prime, so I'm using the third property in that proposition. And this is the same as phi of 2 squared times phi of 5 squared. And now I can use the property of how to compute values of phi for prime powers. So that will be 2 to the 2 minus 1, so 2 to the 1 times 2 minus 1 times 5 to the 1. Let me write a little 1 here to note that I've decreased the exponent by 1 times 5 minus 1. So that is 2 times 1, so just 2 times 5 times 4. So that is 20 times 2, so it's 40. So that's my final answer. Okay, and we can compute values of phi like that. Okay, I'm going to next we're going to do a couple of applications of modular arithmetic, and then after that we're going to move on to finite fields and Fermat's little theorem. Okay, we'll stop there.